Hey guys, happy Monday. Oh, it's Wednesday. It's Wednesday. Sorry. Apparently I started a live broadcast, but didn't actually start it on YouTube. I had no idea that could happen. Hopefully you guys are doing well. Your exam 1 scores should be up on Canvas. The key for that is forthcoming, so you should see it in a couple of days, or maybe this evening. Kind of depends. So today we're going to start chapter 4. Chapter 4 is probably a good turning point for the semester. Hopefully things will kind of start to make a lot of sense when we think about chapter 4. We're going to use some of the information from chapter 3, add in a little bit more. And then once we finish chapter 4, it's really a kind of a different situation for chapters, really 5 through 9. So as we think about that, it will just be kind of this is really the last set of reactions we're going to talk about. And everybody's always kind of excited when we move away from reactions. So in chapter 4, we're going to start to think about what happens in solution. If you have a beaker, what happens when you put stuff in there? What happens when you put 2 things in there? How does that work? So hopefully you guys are doing well. As always, if you have a comment, you can drop it in the comment box, which I think is on that side. I'm glad you guys are making it, kind of trickling in. Sorry for the delay. I had some small complications today, trying to get my YouTube Live up and running. So we're all kind of rolling in, figuring it out. Other things that I have to tell you guys today. It's fall-ish here. It felt really nice the other day. I haven't been outside since I came into the office, so I don't really know what it looks like outside. But if you have any questions, you can drop them over there. I have about 9 questions today that we'll go through. Don't forget, we are back to the usual schedule. So the weekly assignment is somehow posted yesterday, which is okay. You can take a peek at that at any time. So that assignment is due by Sunday night at midnight. Your ALEX objectives are due at midnight as well. So on non-exam weeks, you have assignments due on Sunday night. So you have those 2 due this week. Hopefully it will be pretty simple. You should be really proficient with uploading your work by this point, and your ALEX objectives are back to normal. So in chapter 4, as we start to think about what happens or how things work, one of the things with chapter 4 is we're going to start to talk about something called solubility. So in the slides, this is going to be a little hard to see, and I've written all over mine. There is a solubility guidelines table. You can also find this information. I posted in the exam. It's where the exam, where those equation sheets are. There's like a chapter 3 or chapter 4 handout. This side is the solubility table. The other side is the activity series. We will use both of these in this chapter, so you may want to try to either print it out or recreate this in your notes if you don't print out the slides. So the first question today is on my face, and that's not great. That's okay. So we want to write the balanced chemical equation, the complete ionic, and the net ionic equation for the following reaction. We want to identify the precipitate, so which one is insoluble. So we are going to mix together barium acetate and magnesium sulfate. If you chose not to memorize the common ion table or the periodic elements, this is when that information is particularly haunting. So in this case, we are going to look at first, we want to write down what we have. Not pretty simple, but that's the first instance. So the first thing is we have barium, which is Ba. Make sure that's big enough. So we have barium, which is a 2+, with acetate, which is C2H3O2, 2. So the acetate ion is a -1. So when we think about the acetate ion, we know that we're going to need 2 acetate ions to counteract the 2+ on the barium. So this is aqueous. And we're adding to that magnesium sulfate, also aqueous. Got this word. So when we add these together, the problem itself gives us the reactant side of the equation. Great. So I know that we've talked about how to figure out how to balance things. But this part of the chapter is about predicting the products. So when we predict the products, y'all know I'm from Texas, and if you don't, now you do. I like a good square dance like anybody else. And so in a square dance, they will say, do-si-do, swing your partner round and round, everybody switch. So in this case, the metal ions are going to switch anions. So the way to think about that, in my opinion, is to actually write out the complete ionic. And then you can see, okay, we're just going to swap partners. So the complete ionic, I'm going to move this over just a little ways, give us a little bit more space. Yep. Is where you write out everybody who came to the party. Not just some of the people, literally everyone. So every element breaks up into 2 parts on the left side of the equation. So we have barium, which is a 2+, and then there are 2 C2H3O2-. That's also aqueous. So in this case, it has to come out of the parentheses, and so we just put a stoichiometric coefficient 2. Now we look at our magnesium sulfate. So plus Mg2+, which is aqueous, plus the SO4 2-, aqueous. So now on the left side, we have 4 components. So each compound breaks into 2 components. Now we've talked about this when we think about balancing equations. I pretty much said you have the anion, you have the cation, don't break them up. That is especially true with your complete ionic and your net ionic, okay? So as we make the other partners, what we need to do is think about how the metal ions are going to switch friends. So that means that the barium is now going to coexist with the sulfate. So up here we will have barium sulfate. I still see that. And on the other side, we're going to have the magnesium and the acetate ions. So we're going to end up with MgC2H3O2. Just a little bit out of, there you go. So now that we have this information, we got to figure out which one is the precipitate. Or if you're doing your homework, sometimes there isn't a precipitate, and that's okay. In that case, we write NR for no reaction. So when we look at our solubility table, which basically tells us who is soluble and who is insoluble, a precipitate is a solid that comes out of solution, and that solid is the precipitate. So when we look at this, the acetate ion is always soluble. Well, that's a good rule. So that means this is aqueous. And the barium sulfate, so sulfate ions are mostly soluble, except over here on this side it will say important exceptions. Strontium, barium, mercury, and lead. So this barium sulfate right here is going to be a solid. So this is our precipitate. So if it asks you what is the precipitate, what is the solid, it's asking you who or what is insoluble. So from here, we have to think about the complete ionic on the other side. When something is insoluble or solid, it does not dissolve into its components. Now, on this side, everything breaks up into its ions. Barium, because it is solid, does not dissolve into its ions. It does not ionize. So we have barium sulfate, solid. So solid things cannot ionize into their components, plus Mg2+ aqueous, plus, and then we're going to run out of board space, 2C2H3O2 minus aqueous. So, tilt down a little way, kind of make that work. So, now that we have our complete ionic equation, so this is the complete. It has like all the parts. This is everybody who was there before, and this is everybody at the end. So from here, it asks for the net ionic equation. Now, there are no sports happening right now. Well, there are some. So in a non-pandemic world, if you went to the Jaguars game or any other football game, we believe, I'm a big fan, so I believe it too, that when we yell at the players, it helps them score better, right? Here's the thing. It does to some extent. But when you go to watch a tennis match, everyone is quiet and we just watch the game, right? So a spectator ion is an ion that is present both before and after. So we want to remove them from the net ionic equation. We only want to know who's involved. So any ion that you see on the left and the right of the arrow needs to be canceled out. So in this case, the magnesium we see on both sides and the acetate. So the net ionic equation is barium 2 plus aqueous plus the sulfate ion, SO4 2 minus aqueous, gives us BaSO4 solid. So the complete ionic equation is the second one, where it is everybody in the pool both before and after. The net ionic equation is where we see just the components that are involved in the creation of our solid product. Do you guys have, what questions do you guys have? And if you have none, you can go ahead and write none in the box. I think we have another example. We will talk about why that example is not the best example, and we will fix it here in just a second. I will go ahead and plop it up here while we wait. Nice. It's good to see you today, Nicole. I'm glad you're here. Looks like most of you guys are doing okay. I'm glad these are all going great. So let's think about another example. So when we think about these types of equations, to be honest, they're not all that complicated. The worst part, in my personal opinion, is writing out this entire complete ionic equation. The entire complete ionic equation takes forever because you need to have the states and the charges and any stoichiometric coefficients. It just takes forever. That's my opinion. So let's think about the next example. And that doesn't erase that off. So in this next example, it gives us, we don't necessarily need our polyatomic ions, but it gives us something else. So we'll talk about why the example I gave you was bad, and then we'll talk about how we can make it a little bit more interesting. So in this example, it says we are mixing together iron sulfate and lead chloride. So it turns out that if you, I've tried to fix it and not made it any better. So in this case, if we think about, what did the first one start with? Iron sulfate, SO4 plus PbCl2, and you mix them together. So it turns out that the iron sulfate, FeSO4, is in fact, this could be aqueous, but lead chloride is actually insoluble. So if you mix these two together, there is no reaction, aka nothing happens. So on Alex, they love to ask questions where the answer is like, no. So if you mixed into a beaker of water iron sulfate and lead chloride, nothing would happen. The iron sulfate would go into solution, the lead chloride would stay as chunks at the bottom. That's boring. I'm getting to the sodium sulfate. So, hold on. So when I was like typing everything into this, was like, oh, the iron sulfate is the problem. It turns out that the lead chloride is the problem. So instead, we will make a new problem. So we're gonna ignore everything up here. I will type it in just a second. So in this case, we are going to mix together sodium sulfate Na2SO4, which will be aqueous, plus potassium. Yeah. No. Hold on, I'm trying to come up with another solution. It's not working quite as well in my brain. Yeah, we'll use strontium chloride. Aqueous. So instead, basically what's up here, you can totally ignore. Instead, we're going to mix together sodium sulfate and strontium chloride. This will actually work. So in this equation, we're going to decide what is the complete ionic, what is the net ionic, and what is the balanced equation. So on this one, we're going to do something quite similar to the last one. We're going to write out the complete ionic first. So we're going to take our 2 Na plus aqueous plus SO4 2 minus aqueous plus strontium 2 plus aqueous plus 2Cl minus aqueous. So I'm going to check on the questions here. What do you guys think about this? I've yet to figure out how to type on this. MAR. So when we think about this, we're going to have our dose-to-dose reaction where the sodium interacts with the chloride and the strontium interacts with the sulfate. So in this case, we're going to have sodium chloride, which is NaCl, plus strontium sulfate. And so don't forget, we will need to make sure this is a balanced equation. Ooh, yikes. This doesn't go down here. This goes up here. So we have NaCl plus strontium sulfate. So when we look at our solubility table, we know that sodium chloride is aqueous and our strontium sulfate is a solid. So in this equation, it is currently unbalanced, so we're going to drop a 2 here because there are 2 chlorines and 2 sodiums. So when we continue our net ionic equation, we will get a 2 Na plus aqueous plus 2Cl minus aqueous plus strontium sulfate solid. So Mariah asked, so you can't have a reaction when it's insoluble in the reactants. It's important to think about how if something is insoluble, it is solid inside the beaker. So nothing happens. Think about it this way. If you were making sweet tea and you added sugar, it will dissolve. Not if you add too much, but if you add a little sugar. If you were to add rocks, like you walked outside and you added dirt rocks, those rocks are going to stay at the bottom. They're not going to do anything. So when we think about the strontium sulfate or anything else that's solid, think about it as a tiny rock stuck in solution. When it's a tiny rock stuck in solution, what that really means is that it basically will not dissolve, and that's what insoluble means. So when we come back and write the net ionic equation, we're going to remove or cancel out anything on both sides. Sodium's out, chlorine's out. And so what we're left with is the sulfate ion, SO4 2 minus aqueous, plus the strontium 2 plus aqueous, gives us strontium sulfate aqueous. So you'll notice in this example, these are in a different order. So this has a lot of variety. Basically, you could put stuff kind of in any order as long as it's on the right side of the equation. So in that case, your aqueous and your solid could be flip-flopped. There is no right answer in that case. But a couple of tricks. On the left side, or the reactant side, you should only ever have up to 4 items. So one of the big mistakes that students make is they'll break this sulfate ion into a bunch of parts. It's just the one thing. It's just the sulfate ion. So each component should really only break into 2 parts. That's it. So if you guys have any questions, go ahead and drop it in the comment box. Oh. Yes. So Zara realized, because I got excited writing aqueous everywhere else, that this is solid, and so it should be that way when I wrote it on the board. Sorry about that. Other questions, other thoughts? Thoughts about how to do these type of questions? After this, we're mostly going to do math for the rest of this, thinking about dilutions and molarity. Okay. Doesn't look like and I can't read it when it's like that. So the next thing we're going to start to talk about today is we want to look at solving this question. So what is the molarity of a solution in molar when 12.5 grams of sodium chromate is dissolved in 750 milliliters of water? So molarity is relatively... Ooh, good catch. Mariah, so I think that's who that is. Yeah. There we go. So in this case, molarity is one of the things that students both love and hate. So when we think about molarity, molarity is at heart. That is correct, Mariah. Molarity is moles divided by liters. So molarity, oh right. Hold on, I need a new marker. So molarity is equal to moles divided by liters. So when we think about molarity divided by liters, this tells us that in our questions, it's going to become two things, and then we're going to divide those. So the first thing is we need to determine the number of moles, and then we're going to determine the number of liters. So when we look at this, the ability to convert grams to moles is a skill that we learned previously. So as a reminder, we're going to take our piece of paper. We're going to take our 12.5 grams of Na2CrO4 using the molecular weight, which is just a sum of all of the atomic weights to 2 decimal points out of the periodic table, which is 161.98 grams in 1 mole. When you plug this into your calculator, hopefully we all get 0.07717 moles. So now we've taken a skill that we already know. So now once we have the moles, we need to figure out the liters. So it tells us that we have 750 mils of water. So 750.0 milliliters. There are 1,000 mils in 1 liter. This gives you 0.750 liters. You do not have to show this work. This right here, I'm showing in case you're like, I don't remember milliliters. But if you know that mils to liters conversion is to just divide by 1,000, you're not required to show this. So to calculate the molarity, we're going to take 0.07717 divided by 0.750, and that's going to give us 0.10289 molar, which, once we use our significant figures, which based on the problem is 3, so this will come back to 0.103 molar. So when we think about the concentration of anything, it's the number of moles divided by the number of liters. So as we think about this example, because we're going to do a bunch more, so don't feel like if you didn't get it, you're lost. What questions do we have about this calculation? And if you don't have any, feel free to drop a none in the box. And then we can, I will go ahead in case you did not look at the worksheet. You can start on number 4 while if anyone has any questions. And if no one has questions, that's okay. Molarity is a calculation. So in our next example, we're going to basically do a very similar thing. So we're going to calculate the concentration in molar of a solution prepared, in this case, by 4.28 grams of nickel chloride dissolved in 150 mils of water. So when we think about this, we're going to set it up virtually identically. So we want to first calculate the number of moles, then calculate the volume, then divide one by the other. So when we think about this, the ability to calculate molarity, and don't worry, we're going to do some of the more complicated molarity questions coming up. Maybe don't worry wasn't the best way to say that. But before we think about that, so Camilo asked, how did you know to cut off this at the 5th? I don't understand. Sorry, the fire alarm in the building's going off, so hopefully it's just an alert. Otherwise, it's going to be a really exciting afternoon because I'll teach this outside. Okay. Let's answer those 2 questions. So Sarah's going to take that one. She is fully correct. And Genevieve answers. Y'all. Genevieve asks, will it always be dissolved in water? In Gen Chem 1, we only dissolve in water. Ooh, Mariah, I didn't know you were on campus today. Yeah, there was an alert at 2:45, apparently one at 3:30. Who knows? Glad we're all safe. So, also, if it's actually a fire alarm, we should all exit the building. I'll just carry my computer downstairs talking. It'll be super fun. But, so, it will always be dissolved in water in this class. In other courses, there are other compounds that we can dissolve in. And so both Nicole and Camilo, I just stopped a couple after the number of sig figs. So you didn't have to write that out. You could have done most of it in your calculator. You should have gotten a very similar answer. So let's think about our nickel chloride solution. We have 4.28 grams of nickel chloride. So we're going to take our 4.28 grams of nickel chloride and divide by the molecular weight of 129.58 grams in 1 mole of nickel chloride. And that's going to give us 0.033030 moles. Again, I just kind of extended it out past that just because. If you trim it back too early, you will get off a little bit, or you could be. So our liters in this case, we have 150 mils, which when we divide by 1,000 to convert to liters, we get 0.150 liters. So the molarity is 0.033030 moles divided by our 0.150 liters. When we plug this into our calculator, hopefully, what we get is 0.2202 molar, which with our sig figs, and I think you can still see this, you would get 0.220 molar. Just a little bit off, just like that. Oh, it's terrible. I'm so sorry. I'm so sorry. Okay, any questions about this calculation? I don't really know what's happening with the fire alarm. We'll figure it out as the day goes on. If I knew how to mute myself, I totally would, but I don't. So, if you have any questions about this calculation, let me know. If you don't, we can move on to number 5, which is something a little bit different. Oh, I'll go ahead and put up question number 5. So Billy Ann asks, is concentration the same as molarity? By and large, in Gen Chem 1, yes.
Test. This is a test of the emergency notification system. This is all.
I'm so glad y'all are here for this today. This is so exciting. It's not fun. Okay, so what was I trying to say before he said it was a test? Oh, the concentration is in fact the same as molarity. I will try to ask for the concentration in molarity or ask what is the molarity of this solution. I have tried, and I will continue to do, to pull stuff from Alex or pull like questions from Alex so that you guys can go back and watch this when you get stuck on some of your objectives. So it looks like we don't have any other questions aside from the fact we're all terrified about whoever's doing whatever this is today. So in this case, this other question, which I'm going to actually try to make that a little bit bigger. Well, that didn't work. There we go. I mean, that was the same. So we want to calculate the volume in liters of a 1.1 molar sodium chloride solution that contains 175 grams of sodium chloride. So now we're going to use the molarity. So molarity can be a calculation like this. There's lots of this on Alex. But the next thing we're going to do is to think about molarity as a tool. So molarity as a tool is just a little different than the alternative. So molarity is always moles divided by liters. So, which I'll rewrite what I just wrote. Erased. So in this case, we want to use the molarity to do a calculation. Now, I'm going to show you how I do this. If you watch other videos by other professors, or maybe you learned this a different way in high school, it is my suggestion to stay out of the triad of death. You might be like, ooh, maybe I like the triad of death. I will show you my way. I will briefly tell you what the triad of death is and tell you why not to use it. So, in this case, the question says, we want to know how many liters contains 175 grams. Well, the first thing we need to know is how many moles is that? So we're going to take our 175 grams of NaCl and convert that to moles using pretty much the same way we've been doing it for ages. There are 58.44 grams in 1 mole. So this is going to give us 2.9945 moles of NaCl. Now it asks for how many liters in this molarity. So we have this many moles. If you remember density, this is going to be a lot like density. So we know that 1.1 molar equals 1.1 moles in 1 liter. Now, all I did here was divide the units. I just took them apart. It's kind of like a deconstructed sandwich or anything else deconstructed. Same stuff, I just spread it out. But now I can use this as a conversion factor. So I can take my 2.9945 moles and convert using the molarity, which is 1.1 moles in 1 liter, to give us 2.722 liters, which using these sig figs is 2.7 liters. Now, you might be like, whoa, I don't really know what just happened here. That's okay. So what we did is we took our molarity and put it back into moles per liter, and then we used it like a conversion factor, just like density or anything else. Now, I will briefly show you, well, if you have any questions, I'm going to leave this up. I'm going to move the camera a little bit that way, one of the ways, and then show you briefly the triad of death. Now, the triad of death is called the triad of death for a reason. Because students go in there, it's like the Bermuda Triangle, they don't always come out. So what a lot of students want to do is to set it up like this. 1.1 molar equals 2.9945 moles, and solve for x. Here's the thing. You can do that. I find that students often plug this into their calculator incorrectly. I call it the triad of death because once we start looking at this, it gets a little confusing. You guys also like to do this for density. I don't call it the triad of death there. It's still the triad of death. So I do not recommend this under any circumstance. I call it the triad of death because it's where calculations go to die. So this method, which I will move the camera so that we can all see it and not just see my face. So in this calculation, we will get to the right answer. So as we think about this, what questions do you guys have about doing these type of calculations? Also, if you have none, write none in the box, which It's kind of my new favorite thing to see. So what do you guys think? Good, bad, ugly? Will the fire alarm go off again? I don't know. So Catherine asked a good question. So she asks, why is it 1.1 mole over 1 liter instead of 1.1 mole over 1.1 liter? So in that case, if you were to divide 1.1 divided by 1.1, so you'll get a molarity of 1. So in this case, you can't, typically in here, what we do is we put the molarity number on the top and then just assume it's out of 1 liter. So if you had written 1.1 mole divided by 1.1 liters, that would have actually given you 1 molar, because any number divided by itself is 1. So when we split this out, the over 1 is kind of a default unit. Jordan asks, are we allowed to use the triad of death method? I really can't tell you not to, but what I can tell you is that most students who enter the triad of death do not exit the triad of death. I would strongly encourage you not to. If that is your preferred method, then you can use it. I'm not going to take off points if you use it, but I often find that students use the triad of death and then it does not work as well. So, which is why I call it the triad of death. So Kajal says that she used a triangle. And so if you like the triangle method, there are ways that you can continue to use that. What I will say about all of that is that some of the calculations that we'll do will make that more complicated.
We will be testing the on-call. Please disregard. Pardon the interruption.
Looks like we were all wrong. Fire alarm's back. I wish I had my shades. 1 molar. So in Catherine, 1 molar is 1 mole per 1 liter. So if it's 2 molar, it's 2 moles per 1 liter. So all I've done...
Test. This is a test of the emergency notification system. This is only a test. Conditions are normal. No action is required. Test. This is a test of the emergency notification system. This is only a test. Conditions are normal. No action is required.
Okay. So, Genevieve, I don't think you jinxed it. I think I did by making the joke. I'm so sorry. But this is exciting. I feel like I was saying something super intelligent, and I have no recollection of what it is because he told me it was a test, and like, I just forgot. Everything is gone in my brain. So if you remember what was happening before we watched him tell us it was a test, feel free to drop a comment in the box. Otherwise, we will think about us talking about molarity. Okay, but we're the next. Good, y'all are handling that. So the next thing we want to think about is writing neutralization reactions. So.
Test. This is a test of the emergency notification system. This is only a test. Conditions are normal. No action is required.
Well, this is going to be exciting. I did say that 2 molar is 2 moles per 1 liter, and so you can set all of your equations up in that way. I tend to think about molar just being moles over liter, and so all we're doing is uncoupling the unit. So molarity is just a fancy way of writing moles per liter, which I really think arrived because people would just like mush those words together, and then we made up a unit. So all we did is take it back apart to make moles over liters versus molarity. So that's all that is. So for the next equation, for the next problem, we're going to talk about acids and bases. So if you watch the acid and base lecture, it's quite old. The content is pretty much the same. The biggest thing is that the table of acids and bases you need to know. So how you go about learning those is kind of up to you, but you do need to know the strong acids and the strong bases. So also feel free to make the assumption if it is not a strong acid, it's a weak acid. Like there's no middle ground, it's just one or the other. So the question to ask, what are the neutralization reactions? So when we think about acid-base reactions, they all fall into this pattern. Yep. We have acid plus base gives us salt plus water. So when we think about the first one is HCl plus KOH. So HCl is our acid plus potassium hydroxide. Now, when we talked about the net ionic and the complete ionic, we know that these basically break up into parts. So we know that this will split into the H plus Cl minus, and then we have K plus OH minus, where the OH is the hydroxide unit. So from here, we're going to have our traditional do-si-do, round and round, new partners everywhere, to where we have KCl plus HOH, otherwise known as H2O. Now, you might be like, I thought salt was sodium chloride. It is in common, like, I went to the store and I needed to buy salt. When we think about it in this component, any inorganic salt that is soluble, so this is aqueous, is considered a salt. The state will be a subscript L because it's a liquid. So in Alex and lab, when we have the subscript L, you can treat it like in a net ionic equation as liquid, like as a solid. So it basically becomes water and stays water. So an acid-base neutralization basically is a metathesis reaction, which is where the two partners switch, except what you get on the end is not a product and an insoluble. It is aqueous and H2O. That's all it is. So from here, we are going to go ahead and think about H2SO4 and sodium hydroxide. So in this case, we're going to see a very similar component of NaOH and H plus and SO4 2 minus. So in this case, we're going to do the same thing where we see Na2SO4 as our aqueous salt plus plus H2O liquid. We need to make sure it balances. So we're going to drop a 2 here and a 2 here to get this. Any questions, any comments, any thoughts? What do you guys got going on? Okay, so the question is, what are the states for the other two? They will actually be aqueous under all conditions. Good question. Although sometimes in Alex, it'll say like in this acid solution, someone added solid sodium hydroxide. So in that case, you definitely can go on and move forward in that way. So if the states of those would be determined out of the problem kind of the same way. Other questions today? Nice, I like it when you guys tell me it's working pretty good. So for the next 20 minutes, or however long it takes us to work through this, we're going to talk about dilutions. So dilutions are basically where you take a stock and you dilute it. So dilutions allow us to, so when do we encounter these in like our real life? A few years ago, and every now and again, they made those basically like flavoring that you can squirt into water. That's a dilution. You took a very concentrated solution, mixed it with water to make something more dilute. The way my mom makes sweet tea, you make a very concentrated sweet tea that's frankly kind of gross, and you mix it with water and it's delicious. So dilutions are not something we are unaccustomed to, they're just new. So in this question, it asks, what is the concentration of the stock of lactic acid when 75 mils of the stock is used to create a 350 mil, 65 millimolar solution? So the hardest part with dilutions is figuring out how to set up the equation. Because we're going to use M1V1 equals M2V2 and M1V1, well, that's just one equation. So the important part is to figure out what is the before and what is the after. So if M1V1 equals M2V2, we just need to figure out what is the before and what is the after. So the other thing that's really important is that the before and after are the same. You can do the before as 1 or the after as 1. So in this case, 75 mils of the stock, so 75.0 mils, is going to make a 65 millimolar of 350 mils, sorry. So when you plug this in your calculator and solve for M1, which is M1 equals 65.0 millimolar, multiply by 350 mils, divide by 75 milliliters. So in this case, when you plug this into your calculator, you should get 303 millimolar, which is the right number of significant figures. So Nicole asked, and then we'll go back to this. So if you have questions, go ahead and ask them. So Nicole asks, if the acid or base is a solid to begin with, then there would be no reaction. Actually, if the solid is a strong acid or base, it will dissolve. So when it's only no reaction if it doesn't dissolve. So think about it if you were to add sodium chloride, salt, into water. So the sodium chloride is a solid when it goes in, but then it dissolves into the salty water. So that's all that is. So Kajal asks, we don't have to change the millimolar to molar, only if it asks you to. So in this case with M1V1 equals M2V2, as long as your units are the same, 2 milliliters and milliliters, millimoles, millimolar, or molar and molar, you actually do not have to cancel those out. So the advantage of the M1V1 equals M2V2 is the fact that we don't have to change the units as long as they're the same. So in this example, we can see that the milliliters cancel out on both sides, and then we're just left with the millimolar. Good question. Any other questions today about this? We have some more dilution examples, though. Nice. So in the next question, if you've already solved it, great. If you haven't, you can go ahead and think about that. Kajal asks, before, you can work on this if you're ready, do we multiply or divide by 100 to get to molar? So if you want to go from millimolar to molar, you will divide, there are 1,000 millimolars in 1 molar. So you would divide by 1,000. Good question. Glad to help. I also always write mine out this way, just because it makes it easier for me. So if you're going from molar, you multiply by 1,000. If you are going from millimolar, you don't. Hey, Jordan, in your comment you ask, how was the equation derived? Which equation? The M1V1 equals M2V2 equation? Or are you asking about a reaction equation? While he answers that, we will go ahead. This is on like a rolly cart, so feel free to drop that comment in the box, Jordan, and I will not erase this until you ask or answer that. So in our next one, how many milliliters of a 1.25 molar glucose stock are needed to make 500 mils of 750 millimoles? So we're going to do the same M1V1 equals M2V2 kind of calculation. So in this case, what we're going to do is we're going to set up that we have a 1.25 molar times V1, but the molarity of the other compound is set up as 750 millimoles. So we will go ahead and take our 750 millimoles. There are 1,000 millimoles in 1 molar. So this is 0.750 molar. And our solution is 500 mils. So in this case, V1 is equal to 300 decimal point milliliters. Okay, so Jordan asked, you are asking about the M1V1 equals M2V2. So that equation was determined, it's kind of like an aside answer, but based on so you can do the long way around, where you take millimoles and liters and convert to moles, and then take the other volume to calculate the molarity. So you can set it up in a more roundabout calculation, and I think I go through that in the dilution video. So in that lecture, I believe it goes through that calculation of how this was derived. But because these units are the same, so if molar is moles per liter equals moles per liter times liters equals moles per liter times liters. So that gives you moles equals moles. And so the quantity of moles in the stock and the quantity of moles in the dilution are in fact the same. So M1V1 equals M2V2 basically says that the number of moles is the same. We've just changed the volume. And so you can think about it this way. Does that answer your question? Does anyone have any questions about the glucose example that's on the other side of the board as well? It doesn't look like it, so I will go ahead and throw up question 9. So in this case, a chemist makes 780 mils of a barium chloride solution by adding distilled water to 170 mils of a 37.4 millimolar stock, what is the concentration of their new solution? So this is going to be quite similar to all of the rest of the solution questions. So we are going to just erase this and set it up this way. So in this example, we still are going to use M1V1 equals M2V2, which is a great option. So on the left side of the equation, what we're going to see is that we have 170 mils of a 37.4 millimolar solution. And we don't know the second, or the molarity, that's what we're looking for. And the last thing is going to be the 780 milliliters. So in this case, we're going to solve for the second molarity, which is 8.15 millimolar. So M1V1 equals M2V2 is really fantastic. And I'll move out of the way so you can see it. The biggest complication with M1V1 equals M2V2 is that it doesn't actually always, it's not always relevant. So in order for this to be true, it has to be a dilution. So next week, we're going to talk about titrations. And there are some online videos, not mine, that tell you that what you can do is set it up in a way where it's, it's just an M1V1 equals M2V2. That doesn't always work. It does sometimes. But a dilution has to be the same type of molecule on the left and the right. So the before and after need to be the same chemical component. So what questions do you guys have about the material from this week? What questions do you have about any of the examples we've done today? That was the last one. So I will hang around and answer any questions you guys have. If you have none, y'all have a great week. Don't forget to do your weekly assignment. And don't forget to do your ALEKS objectives. So Mariah asked, hey Mariah, you asked, never mind. Okay. So Catherine asks, in the 4.3 video, I didn't understand gas release at all. So a gas release only happens under certain conditions. This semester, I am electing to kind of leave that to the wayside. If you are taking in-person lab, sometimes when you mix solid components with acids and bases, they will evolve off a gas. Basically, it will bubble. Ways that you might see this happen in real life are Alka-Seltzer tablets. Back in the 90s when I was a kid, all of their commercials were people dropping those in water and it bubbles. So in that case, it is just a gas evolution. So the way you can know that it's a gas evolution is that one of the products is CO2. In the grand scheme of things, in this semester, this time, we're not really going to talk about gas evolution at all. We may see those equations again when we talk about the gas laws at the end of the semester, but otherwise, I'm not saying they're not important, but they probably won't show up on the test. So you can take that for what you will. So we don't have to learn. So Nicole asks, we don't have to learn oxidation reduction reactions this week or concentration So the oxidation reduction reactions, you can think of those as just a type of reaction. So I like to think about it like we've learned thus far. Basically, 5 types of reactions, I think, maybe 6. Combination, decomposition, combustion, metathesis. Oxidation reduction is a component of that. We'll talk about those some next week. And then the acid-base neutralization and the acid-base gas evolution. So I lied, there are 7 types of reactions. So those 7 are basically the types that we see in chemistry. So we will talk about oxidation numbers, which are important for oxidation reduction reactions. If you've read along in the textbook, which I always advise, they talk about redox reactions for like 1 paragraph, and that's about all she wrote. So we're not going to talk about those. In some of the videos, it mentions that they are there, but you don't actually need to do that in any way, shape, form, or fashion. So, but the concentration of solutions, we talked about that first. Second. So that is the molarity. So are you talking about a different concentration of solutions question, Nicole? Is she still around? Glad to help. And it means a lot that you guys will write in the box, like, hey, yeah, I got that. Any other questions? Any other thoughts? If you have questions, send me an email. Come to office hours. Any of the above. Otherwise, I will see you guys next week, and hopefully there will not be any fire alarms. Y'all have a fantastic rest of your day, and I'll see you soon. Oops.